Each week, in picking stories for this show, I look at a lot of places. There's the stereotypical. I check out what people are gabbing about on social media. There's the classic. I review press releases coming out on Eureka Alert and other services. And then there's going a bit deeper. I look at what is coming out of conferences and coming out of journals. Most weeks, I love learning new things, and this story-picking journey is usually something that exposes me to things I just love, like archaeology, animal science, and random dinosaur updates. I am here for the paleontology people. I am here for it. But some weeks, I see stories I feel I should cover, and then I don't, because I, as a human, just can't. This last week, there were a bunch of new papers on various aspects of climate change, ranging from how Greenland is actually becoming green as its ice melts to the implications of lowered sea ice levels in Antarctica to the plight of polar bears. There were multiple papers on that. These stories on polar bears caused me to nope right out, to go looking for candy, and then learn my husband had eaten all of my peppermint patties. I just wanted something that didn't hurt. And the news that's coming out of climate change hurts. As a space scientist, as a journalist of space science, I rarely have to deal with widespread human suffering or even potential human suffering in my stories. My colleagues who cover wars, pandemics, and economics, I don't know how they do it year on year. This week I realized that when it comes to international politics and war, space could be the new frontier. And my safety in covering space science may be coming to an end. In a story covered very well by the Washington Post and discussed by the Atlantic Council, we have learned that Russia is developing a space-based nuclear weapons platform. According to Washington Post and CNN sources, the goal isn't to target satellites with missiles as we've seen done with conventional weapons in the past. Rather, the goal is to detonate a nuclear weapon in an area of orbit that will cause a matrix-style overload of electronics that kills all the satellites in the local sphere. Depending on what altitude this kind of a detonation occurs at, the EMP blast could also affect the surface of the Earth. Over on Astronomy Cast podcast, Fraser and I discussed the story in a fair amount of detail, and we put it in the context of the International Partial Test Ban Treaty and the 1967 Outer Space Ban Treaty. This week, here on this show, instead of discussing those things, we're instead going to discuss atoms, exoplanets, the structure of atoms, and the evolution of supernova 1987A. We're going to take you not just out of this world, but out of our solar system. We're going to visit my happy place, and I hope it is your happy place too. This is Escape Velocity Space News. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Late one night last week, I was binge scrolling science on social media when I stumbled across reports that initial analysis of Bennu samples indicated that it was made of debris from an ocean world. As a child of the 80s, I think of Earth as an ocean world, a water world. A pale blue dot covered in oceans and home to whales that one day Mr. Spock will bond with and transport to the future, or something like that. And I wasn't the only one thinking like that. Another human whose name is withheld to protect their identity posted about how wild it would be if OSIRIS-REx had flown all the way to Bennu, only to discover a bit of Earth that got splashed into space with some dinosaurs. And I went to sleep hoping that would be exactly what had been discovered. And this is how I learned that today, ocean world refers to small moons and objects like Pluto that have ice shells over liquid oceans that are kept warm by very violent physics. Earth is a terrestrial world. Compared to tiny moons like Enceladus, we just don't have all that much water as a function of volume. In a citation that brings me joy, the Guinness World Records notes, quote, "Models based on the gravitational field of the moon suggest that Enceladus, its ocean, may have a volume of roughly 15 million cubic kilometers," end quote. With a 500-kilometer diameter, this makes it 23% ocean by volume. Newly acknowledged water world Ganymede is 46% water. They still aren't mostly water, but they got water. Meanwhile, Earth, the Guinness record holder for total amount of water, has 1,361,620,510 cubic kilometers of water, which is just 0.125% of our world. We are, by volume, not a water world. We are just a rock covered in water. So, back to Bennu. Bennu, much to my sadness, is not a pile of rubble that resulted from something bad happening to Earth or an Earth-like ocean world. It is instead a rubble pile made from the destruction of a world like Europa or Enceladus or maybe even giant Ganymede. At some point in our solar system's past, one of these ocean-filled worlds, it got the structure knocked out of it, and the remaining gravel pile became part of what is now Bennu. And while this story is less human-centric than if that had been a gravel pile of Earth out there, it is actually scientifically super important. We can dig around on our world and the moon and study our origins pretty well. We can't, at least with our current technology and science funding, go out and dig around on any of those ocean worlds out there. Bennu is thus giving us a chance to study the stuff of planets we won't be able to visit for a decade, and even then won't be able to dig chunks out of. This is new. This is exciting. I still wish it was a piece of Earth that was ejected in the demise of the dinos, but I just like dinosaurs. Water is kind of common in our solar system. We see it in craters on the moon, the poles of Mars. Earth has water in all its phases, and as we look toward the outer solar system, there are icy objects galore. The thing is, we know that in our solar system, the sun was hotter, misbehaved, and generally blasted water out of the inner solar system when it was young. So the water we see here on Earth and on other inner objects had to be brought to us after the sun very literally cooled off. Where that water came from is one of the most interesting questions planetary scientists are working to solve. A new paper in the Planetary Science Journal with first author Anicia Arredondo may have an interesting answer. Using data from the now retired Sophia Airborne Observatory, researchers looked at a series of asteroids to see if they could find water ice using the same techniques used to find water ice on the moon with Sophia. And they could. On the silicate-rich asteroids Eris, Melpomene, and Masalali, they were able to see hydrated minerals. And on Iris and Masalali, they found the unambiguous signature of molecular water. This indicates that impacting asteroids could have brought water to our world in the past, which we suspected, but now we know with more certainty. One of the key issues with discovering that Bennu is made of bits of an ocean world and that asteroids had to bring water into the inner solar system is that it implies things had to move around a lot. This problem is exacerbated when we look at alien solar systems and see gas giants snuggled next to stars, a lack of planets with masses between Earth and Uranus, something has to be going on that shuffles worlds around and somehow kills off super-Earths. Analysis of the systematic data acquired by the Kepler Space Telescope shows a distinctive lack of planets around two Earth radii. These planets were detected as they passed in front of their home stars. By looking at how long it takes the planets to go from not in front of their stars to totally in front of their stars, scientists can measure their radii. And while we see plenty of super-Earths and quite a few sub-Neptunes, the two Earth radii systems just aren't there in expected numbers. By combining models that discuss how planets behave at different distances from their sun with an analysis of possible planetary migration routes, researchers led by Remo Byrne discuss how cold planets moving inwards can expand out past two Earth radii as their ices melt and their atmospheres expand out, and potentially get blasted away by stars. In the other direction, a world at two Earth radii that's moving outward will shrink down as the atmosphere freezes out into ices, making it shrink. No matter where you start, these two radii worlds are not long for this universe once they start to move. This work appears in Nature Astronomy. To understand better if this theory is the final answer, we're going to need to better understand what worlds are made of. As JWST continues its work and is joined by large ground-based friends, we can get the needed data to confirm we're on the right track. After the break, we're going to take a look at atoms and the wished-for but apparently missing island of stability. It is possible to buy stickers, sweatshirts, mugs, and all manner of other stuff and things emblazoned with the simple phrase, "We are star stuff." This phrase was popularized by Carl Sagan, and it serves as a gentle reminder that all the complex atoms, by which I mean most everything heavier than helium, well, those heavier atoms found their start either in the nuclear core of a star or in the nuclear explosions of a dying star or stars. But like with so many things, the truth is much more complicated than the meme. The Big Bang created hydrogen, helium, and trace amounts of lithium and beryllium. Stars readily fuse carbon, nitrogen, and oxygen. And as you get bigger and bigger, they can create things as complicated as iron in their cores. Everything heavier than that is formed through drama. And in this segment, we're going to look at just what that drama involves. There are basically two ways to build larger and larger atoms. You can either slam small atoms together and hope the protons and neutrons mostly stick together, or you can flood an atomic nuclei with neutrons and wait for some of those neutrons to decay into protons and give you that larger atomic number. Atoms are defined by the number of protons in their core. Carbon has 6 protons, iron 26. Plutonium, it has 94. The variety of an atom is further defined by how many neutrons that atom has. For instance, the variety of carbon we use to measure the age of archaeological finds has 8 neutrons. And since 6 plus 8 is 14, we call that form of carbon carbon-14. Similarly, the kind of plutonium used in radiothermal generators in spacecraft like Cassini, it has 144 neutrons, and since 144 plus 94 is 238, we call it plutonium-238. Different atoms, those carbons, plutoniums, and leads, have a variety of different possible numbers of neutrons. While we know of 118 different possible atoms that we line up on the periodic table, those atoms collectively come in 270 different stable varieties. And we've observed more than 3,000 different nuclei if you include the unstable varieties. The difference between stable and unstable all comes down to how the atoms are constructed. Within the atom, the protons and neutrons are arranged in shells. And like any DIY project you might have built, the atomic nuclei are most stable when a given shell is full. And if things are built wrong in just the right way, chunks of atomic nuclei will pop off when given the opportunity. This is where we see some atoms just fall apart, while others, like iron, can seemingly hang around for the ages. The sizes of the shells the atoms are filling with protons and neutrons can take some mighty jumps in size. From a nice, stable, full shell at 50 particles, it jumps up to 82, and then 126 and 184 particles, making up a full shell. Looking at the periodic table, this is the jump from tin to lead, and then to a place where we have not yet found atoms. It had been predicted that there should be, an island of stable atoms if we can just somehow slam together a big enough atomic nuclei to reach that next full shell. But the more we explore our universe and the more we create things in labs, the more it looks like we will find more stable atoms, ones that will last half a minute, a few hours. But we won't actually find stable atoms out at these extremely large sizes. For instance, the atom lawrencium was first created by Lawrence Berkeley National Laboratory and the Joint Institute for Nuclear Research. With 103 protons, it has no fully stable version. But lawrencium-266, with 163 neutrons, is stable for just over 22 hours and has actually been detected outside the lab. It was detected as part of a neutron star merger observed in 2017. This particular atom has a number of protons that create a full orbital for its outermost shell of protons. It's not a full shell, but it's a full part of what makes up a shell. Its neutron number is also creeping toward the next magical number at 184. And there are indications that the atom is getting more stable with the more added neutrons. But in a new paper appearing in Nature Review Physics, scientists led by Odile Smites admit that we're not going to find a new row of stable elements to add to our periodic table. It's unclear exactly why that mythical island of stability that we thought physics predicted doesn't seem to actually be there. But if it was there, they say, we should be seeing signs of it. And we just aren't. And this is where it may all just come down to timing. Enough protons and neutrons have to pile up in one place to form a giant atom, and they have to come together so fast that smaller stable atoms don't have a chance to form out of all that piling up stuff? Atoms form in a couple of different ways. The most familiar way is to smash small atoms together. And at a certain level, a rogue proton is a hydrogen nuclei. You have to smash small atoms together so that they have an opportunity to form heavier atoms. Smush enough hydrogen atoms together in just the right circumstances, and you'll eventually get to helium. Smush enough helium together in just the right circumstances, and you'll start to get beryllium and carbon. This is the stuff of stars. And you, my most wonderful audience, are mostly carbon, which is the stuff of stars. So you are actually mostly, not entirely, star stuff. The other way to grow atoms is to take advantage of the instability of neutrons. These chargeless bits of matter will readily split into a proton, electron, and antineutrino. Leave one alone on an imaginary shelf and boom, give it enough time and its 10-minute half-life is going to earn you a small bundle of not neutrons. In supernova explosions and the mergers of neutron stars, we can end up with rapid outflows of neutrons. The flux of these particles can quickly drive the number of neutrons in an atomic core to ludicrous levels, and then they decay, which gives us really cool heavier atoms. For instance, in merging neutron stars, a regular, totally stable atom like iron with 26 protons and 30 neutrons can get bombarded with neutrons until it has transformed into something like gold with 79 protons and 118 neutrons. And gold is just the start of what can be created. But at a certain point, it is just starting to look like this rapid neutron bombardment process just can't get us to that wished-for island of stable massive atoms beyond the edge of our known periodic table. We will probably keep making bigger and bigger atoms as technology advances. But the universe just isn't going to be the one to provide. As a side note, for the completionists in our audience, while the vast majority of our heaviest elements form either in supernova or neutron star mergers, not all atoms require violence to grow. In dying low-mass stars, still dramatic, neutrons can, one at a time, crash into atomic nuclei. And this slow bombardment can cause atoms to creep one atomic number at a time up through the periodic table. It's slow, but it gets the job done. That's it. That's how atoms form, or don't form, as big as we'd hoped. Up next, it's time for rockets and robots imitating bugs. I promise it is space-related. Stay tuned. Americans probably won't be making their way to the moon for several more years. That may be an understatement. And it turns out this is likely a good thing. All this extra time is making it possible for cool new technology to get developed. And some of those tech developers are actually university students who are taking inspiration from some pretty buggy places. In the University of Arizona Department of Aerospace and Mechanical Engineering, a team of students led by Jenkin Thanga is developing structures made from what I can only describe as smart sandbags. And as a reminder, lunar regolith counts as sand, at least as far as filling sandbags goes. Using sandbags in building construction is an idea that goes back to the 1980s, when architect Nader Kahili proposed the idea to NASA and developed the idea on Earth as super adobe sandbag construction. It doesn't use your parent sandbags. This construction uses tubes filled with sand or dirt to construct graceful rounded structures that are fast to build, low cost, and super well insulated. They have also proven themselves robust in the face of earthquakes up to magnitude 7.2. The structures Thenga's team are designing for the moon will contain sensors in addition to sand. These will allow their placement to be tracked by robots and their conditions measured, whether those conditions include thermal effects, vibrations, or, hey, I was hit by a meteor. Since these systems will be robot constructed, I'm hoping that the current experiments in Earth's desert will get replicated on the moon in advance of the arrival of astronauts. What I love about this work is how it has taken inspiration from insects. Super adobe domes around the world look like beehives and have similar thermal characteristics to your stereotypical beehive dome. The new structures being built are modeled on termite mounds, which are used to thermoregulate vast underground structures built by bugs in some of the most extreme desert habitats of Africa and Australia. I'm not always a fan of swarm bots. I've seen a few too many seasons of Stargate to be comfortable with swarm bots having access to random human structures. But I like the idea of swarm bots preceding humans to the moon, doing our construction, and then taking a step back to exist as a piece of history. Time will tell if that's what happens, but I can dream. For now, I'm pleased to welcome on aerospace correspondent Eric Mattis for this week's Tales from the Launchpad. Hey, Eric.
Hi, Pamela. It was another light week dominated by SpaceX launches. On February 14th at 22:30 UTC, a Falcon 9 launched the USSF-124 mission to orbit from Cape Canaveral in Florida. Let's watch the launch.
5, 4, 3, 2, 1, ignition, and liftoff. Go Falcon, go 124. Vehicles pitching downrange. F1D, chamber pressure nominal.
It consisted of 6 satellites from the Space Development Agency, 2 new ones called Hypersonic Ballistic Tracking Space Sensor for detecting missile launches from space, and 4 other missile detection satellites that weren't ready for the previous SDA Tranche 0 launch a few months ago. The booster successfully returned to a landing at LZ-1, which we can also watch.
Stage 1 landing light deploy.
Next up is Progress MS-26, a Russian cargo resupply mission to the ISS, which was launched from the Baikonur Cosmodrome in Kazakhstan on February 15th at 3:25 UTC. It carried 2,518 kilograms of supplies, including science experiments, food, and consumables for the station, such as propellant, water, and gas bottles. Docking is planned for 2 days after launch. Later the same day was the first launch of Intuitive Machines' Nova-C commercial lunar lander from Kennedy Space Center on February 15th at 6:05 UTC. The launch was delayed once after problems fueling the lander caused a scrub on the first launch attempt. Let's watch the launch.
5, 4, 3, 2, 1, ignition, and liftoff. Go SpaceX, go IM-1 and the Odysseus lunar lander. Vehicles pitching downrange. Stage 1 propulsion is nominal. Nominal power and telemetry.
Unlike most leisure landers, it uses cryogenic fuel, specifically methane and oxygen. SpaceX had to specially modify 39A to accommodate fueling this payload, so they already have some methane infrastructure at 39A for future Starship launches. The first Nova C was named Odysseus. It will carry several NASA and commercial payloads to a crater on the lunar South Pole named Malapert A. It will take a very short period to travel to the moon compared to other recent lunar landing attempts because of its cryogenic fuel, just over a week. As of when we're recording this, the landing is scheduled for February 22nd. There was also one classified Russian launch and a Starlink launch that was the 300th Falcon 9 launch overall. We track launches with the help of RocketLaunch.live. So far this year, the United States has had 16 launches, China has 8 launches, Iran has 2, India, Japan, Kazakhstan, New Zealand, and Russia each have had 1. This makes the total number of launches so far this year 31. Finally, there are 9 toilets in space.
Thanks, Eric. I have to admit, this next story makes me feel old. 36 years ago this week, on February 24th, 1987, astronomers Ian Shelton and Oscar Schulze on the Las Campanas Observatory in Chile and amateur astronomer Albert Jones in New Zealand were observing the nearby Large Magellanic Cloud when they noticed an unexpected bright light. This was the first supernova to go off in the vicinity of our Milky Way in the era of modern detectors. I was in 7th grade at the time, and I had my first telescope and was very sad to live on the wrong side of the planet. But also, it was winter in New England, so I wasn't that sad. The light curve and chemical signature of the supernova allowed us to realize it was a Type II supernova caused by a massive star that produced a significant amount of energy through nuclear decay. Thanks to its nearby location, astronomers have actually been able to measure the total mass of various radioactive materials produced during the supernova and track them as they have decayed away. After the launch of Hubble in 1990, and the launch of corrective lenses in 1993, this supernova, cataloged as 1987A, became a regular target of observation. Generations of astronomers have now spent entire careers watching this star change in real time. Now, astronomers are tuning in with the JWST to see what they can see in the infrared. And this is just in time. As the nebula cools, it is fading out of easy detection by optical systems. JWST's infrared observations are going to extend our ability to watch this supernova remnant evolve far into the future. And this remnant still has lots of secrets to tell, including a secret about what is at its heart. Type II supernovae, like this one, should have a neutron star at their core. All indications seem to point toward such a star forming inside of supernova 1987A, but it is likely still surrounded by too much dust and gas to be seen, because we're not seeing it. Telling the neutron star story, that is left for future generations. And that's it for now. Good night, everyone. And remember, go look up.